So light waves are transverse waves. Light waves, that means that the particles of the waves are oscillating perpendicularly to the direction of the wave path, and they are electromagnetic waves. And what that means is that they've got an electric field around them, or they're more to do with, well, they're carrying some sort of electrical energy, and they've got a magnetic energy as well, right? And those waves are, or they're propagating, those electric and magnetic fields are propagating as transverse waves, and they're at a 90-degree angle to each other, or they're perpendicular to each other. And more importantly, what waves are, so we talked about this yesterday with the other class, it was section 1 of physics, but light travels, or waves require a medium. Now, sound can travel through air, sound can travel through everything on earth, but once you go into a vacuum, you won't be able to hear a sound. Why? Because there's no physical particles present. However, light is able to travel through space, so that means that there is a certain particle that's present, because a wave requires some sort of a medium to travel through, and that's where that photon part comes in. That light is essentially a photon traveling through a vacuum, and a photon is a massless particle. And if you kind of read more into it, you can find a lot more information. It's all to do with, so the movie that we watched before, what was it, the Einstein and editing movie, that was to do with, so Planck and Einstein, and they were all working on kind of this light photon thing, that they proposed that light travels through this particle, and they proposed that it was a photon or something. Right. So the next thing that we kind of talk about, that, well, light has many parts to it. We have the visible light spectrum, so right here, these little colors that you see, but on the other hand, it does have this non-visible part, which includes your infrared region, so the heat that you feel from your lamps, it's due to what, it's this infrared radiation that you're feeling. And then you've got microwave and radio wave, right? And essentially they're what? They're still waves. They're doing what? Wave is what? Wave is a disturbance, and it's a disturbance due to energy. So wherever you see waves, the waves are essentially transferring energy from one part to another part, or a source to a sink in this case, or the part that absorbs energy. So you've got radio waves, microwaves, infrared waves on one end of the visible spectrum, and on the other side you've got the ultraviolet region, or the X-ray, and the gamma ray region, or those are radiation types. Now your radio waves, microwaves, well, they're used for communication, more or less, right? And then on the other hand, you've got ultraviolet and X-ray and gamma radiation, which are being used for medical, more or less medical. They've got medical uses. Now, we've all had X-rays done at some point in our life. What is that? That's a high energy source that's been impacted, and what it does, it reflects off of your bones or high density medium, because it's unable to penetrate those bones or whatnot, or high density medium, and they're reflected back, and that's what is being captured on the photosensitive film, right? And that's what you see on your X-rays. On the other hand, what you've got is your gamma radiation, and that's what is, I believe, at some point used to kind of kill cancer cells or whatnot, right? But more importantly, what you see here is the wavelength scale, right? So as you go from radio waves all the way to gamma radiation, you're reducing the wavelength, right? So when we're talking about radio waves, why do we use radio waves for transmission of data? Is because you've got a larger wavelength, and a larger wavelength would mean that the single wave could travel a much longer distance, so you don't have to expend a lot of energy in order to create that transmission. On the other hand, you've got these high or very small wavelength waves, or light waves, And what they're doing is that they require a lot more energy to be processed, because you've got a lot of waves that you'll need to pack in before it reaches wherever you're trying to get them to, right? And that's where this little other infographic comes in, that it gives you a bit more detail what type of radiation it is and what type of their uses are. The previous slide was more of a scale reference. This is more to do with, well, what the frequency is going to be. So you can see that the frequency here is much larger. I'll compare here for the gamma rays compared to your radio waves, whereas your wavelength was what? Wavelength was much larger for the radio waves and much lower for the nuclear reactions or the gamma radiation or the X-rays, right? And that's how we're using them, right? And that usually means that the higher frequency it is, the more energy is being transferred. The reason behind that is that because the wavelength is much lower, you've got a higher frequency, and what that means is that you've got a lot more waves impacting the object in a given time, and that means that you've got more energy being transferred at that point, right? And that's why you get, well, you've got a higher frequency and a more energy or more energetic wave, or more energy is being transferred at this point, right? So now let's talk about light wave reflection. You've all observed this. Light is reflected back at all times. What you see as in colors, like I mentioned before, or what it's that particular light or that mixture of light is being reflected back. So if you're looking around, if you're whatever paint color your walls are, that's a light wave that's being reflected back, or it's a combination of those light waves being combined together and that's being reflected back. The rest of the colors are being absorbed, right? On the other hand, mirrors do what? A mirror is able to reflect everything back, right? And that's why you see everything that's mostly being reflected back. And well, there are different types of reflections that may occur. Have you noticed one thing, that the surface of the mirror is very smooth, right? Or if you're able to polish a piece of metal or sand it down, it will start creating a reflection. And that's essentially doing what? You're trying to get rid of this little diffuse reflection part that's happening, and that's because of this surface abnormalities on the surface of the mirror. Now that could be because of they're easily visible on a piece of metal, but not on the mirror itself, right? And that's more to do with, well, let's see here. So the reflection of light waves from a surface which has surface abnormalities, or it's got a rough surface, and rough surface we're going to talk more about, that's known as diffusive reflection or diffuse reflection, whereas if you've got a smoother surface, you've got specular reflection. That means that a light wave will come in and then it will bend, or it will reflect at a given angle. When we're talking about smoothness, then smoothness is to do with, well, how much the surface variation is based on the wavelength of the incident wave. So remember again, let me scroll back 2 more slides here. The visible spectrum here has a wavelength of, well, around 0.5 into 10 raised to the power negative 6 meters, or around 0.5 micrometers. So it's very small. So when we're talking about surface abnormalities or surface roughness, in this case, a smooth surface would have something which is much smaller than a micrometer. So the differences in between the height or the surface level of the surface would be somewhere on the nanometer scale, right? And that would create a much smoother surface, and that's what glass allows you to do, because it's a different material and it's more smooth on the top of the surface. And that's how it's kind of created. So what happens once you've got a wave coming in? What will happen is it will reflect at a given angle on a smoother surface, or a specular reflection, and that's what we're going to do in physics. We're not going to diverge from this part. We're not going to go into diffusive reflection, but we're going to talk a lot about specular reflection. the way that that angle is that, or that light wave is reflected, is that an incident ray comes in and it's reflected back, and it's reflected back at an angle, and typically that angle is the same as your incident angle from, if you were to draw a line perpendicularly to the surface of the mirror, right? So if let's say this incident ray was at an angle of 30 degrees to the normal, or to the line normal to the mirror surface, it would be reflected back at an angle of 30 degrees as well. So this total angle would be 60 degrees then. And that's an important rule when it comes to light wave reflection, right? So a few things that we will discuss before we move on to lenses, that we've got flat mirrors, and we've got concave mirrors, and then we've got convex mirrors. And well, the important part is that, well, the image could either be real or it could be virtual, and it all depends where the image lands up, and we're going to talk a bit more about it. And more importantly, you can kind of guesstimate or estimate where the image is going to be, what the image distance is going to be, right? Have you ever noticed in your car rear view mirror that the object's a bit smaller, the one in the cabin? Yes or no? Right? The reason why that happens is because of this little artificial distance that has been created, because that object within that mirror is much further than it kind of actually seems. So on the other hand, you've got these mirrors your side mirrors are magnifying the object, and that's what we're going to talk about and how they kind of do it, right? So the first thing that we do is a flat mirror, and what a flat mirror does is, if you were to observe, I'm sorry for the bad quality image here, but what you've got here is that, and on a flat mirror, an image would be kind of reflected back in a straight line. So you have that image that's kind of inverted in plane, so your left side becomes the right side of the image and whatnot. But other than that, everything is reflected back as it is. And the way to do it, or the way to get an idea of where that image is to use ray diagrams. And we're going to talk about how to construct a ray diagram. So let's start with our surface, so table and a mirror. And let's start with an object. So we've got a pencil here. The way that you do it is, well, let's start with a line, or what we've got this is, on this side we've got the real space, or the actual space, and beyond the mirror you'll get this little virtual space, or within the mirror itself, right? And we kind of know that the pencil would appear somewhere at some distance from this flat mirror inside this virtual space. Well, how do you measure, or how do you get this distance? Well, one way to do it is, well, let's start by drawing a line from one location of the pencil all the way lengthwise, or perpendicular to the mirror surface, right? Now the second one is to, well, draw a line that's at an angle to the mirror surface. Once you do that, what happens? What is the rule for a specular reflection? Anyone? What was the rule for specular reflection? The rule for specular reflection was that the angle that the incident ray of light comes in, it's going to be reflected by the same angle if you were to draw a line normal to the surface of the mirror. So let's draw that line. So you've got this normal line that's happening, so you've got that incident angle of the light. The reflected light is going to be, well, or the reflected ray of light is going to be what? It's going to reflect back at the same angle. So we've got theta dash here, but essentially this theta angle equals to this theta dash angle. Now we can extend this line back, the one that's just been drawn for the reflected ray of light, all the way back into virtual space. Right, wherever these two lines, so the first ray of light that went straight through the mirror, and the other one that's reflected back and extended back into virtual space, wherever these 2 points intersect, well, that's the location of this image here, and that's where you can draw your pencil. Right, and you can do this for all the points. Now this is for a straight or a simple image. If this was a curved surface, you would have to do it for each point, essentially where that point is, and you would get that location. But you can create that, and then we can start talking about, well, what's going to be the height. And since it's a flat mirror, you're going to get the same height as the original object, and you're going to get the same distance, more or less. So what you can get here is that your horizontal distance between the real space and the mirror and the virtual space and the image are going to be the same. So P is equal to Q. Your incident ray of light at an angle to the mirror is reflected back with the same angle. So your theta is equal to theta dash, and the height of the object, or the actual object, is equal to the height of the image in the flat mirror, or H is equal to H dash. Right? Or right? Any questions with this? So for a flat mirror, what you see is kind of what you get. You're going to get the same sort of dimensions and the same angles and whatnot. So there's going to be not a big difference there. But let's move on to our, well, so this is how it kind of goes through, and this hasn't been posted on Classroom yet. Once we're done with this, I'm recording a video, I'll process that video, and everything will go on Google Classroom with this. So next we're going to talk about concave mirrors or curved mirrors. That's a concave shape, so let's have the same thing here. Let's draw a line here. Since this is a curved mirror, it will have some center about which this mirror is curved, and it's going to have a radius. This little line is also known as, or the line that passes through the center is also known as your principal axis. Right, now let's take the same pencil again. Let's put it down on the principal axis, and what will happen now? You are to follow the same rules, that you have to first create a light wave that is perpendicular to the surface of the mirror, and then you can draw any incident light on the surface of the mirror other than the perpendicular angle or the 90-degree angle, and it will be reflected back. And that would, wherever those two lines would intersect, that's where your object is going to be. So now, where would you think the perpendicular incident ray of light should go? Remember, this is the inside of the mirror, so the line is supposed to be perpendicular to this surface. So wherever you think it's going to be perpendicular, you're going to draw that line. But more importantly, you have to draw a tangent at every given point on this surface of the mirror. So again, we've got a real space and a virtual space. The 90-degree or the straight line or the perpendicular ray of light is going to act in this direction now, right? And it's going to pass through the center of this curvature here, right? Because this is, if you think about it, if this ray of light went through here as a straight line, it's not at 90 degrees to the surface of the mirror. It's going to be reflected at some direction. You have to find a location where that is going to be at 90 degrees to the surface of the mirror, so you have to draw that, and that ray of light is going to pass through the center of the mirror itself. Now you can take any other position on the mirror and sketch a line. Remember, that angle is going to be the angle theta. You draw a line that is perpendicular to the surface of the mirror. Now this line is perpendicular to, right at the center of this location, or at 0 degrees, and that's why we choose this, because it becomes easier for us. And then it's going to be reflected back with the same angle. So that those rules are still there. But more importantly, what it will do is it will create an inverted image. So if you've got a spoon next to you, you look into the spoon, what happens? You can see yourself, but you're inverted within the spoon, right? And the spoon there is acting as what? It's acting as a concave mirror at that point. And then you get a virtual or an image or an inverted image of yourself if you're looking through at the spoon. So that's one quick way to kind of test this scenario, right? But more importantly, what happens to these distances then is that, well, you've got this little distance here, P, that is kind of in level with this line here, or principal axis, or the back of the mirror. And then you've got this Q length for the object space, and they are not going to be the same, right? And then we've got this one more length, which is the focal length of the mirror, right? And that's where all the light is going to be focused, and it expands back. That point is known as the focal length, and typically this is half of the radius for a concave mirror. So we've got these little equations then that come in. So we've got the relation between the distances, or the object distance and the image distance, and that equals to 1 by the focal length, right? The radius of the mirror is, or radius of the curvature of the mirror is 2 times the focal length of this mirror, or is equal to 2f. And then we've got finally the magnification of how much magnified the object is going to be, and that's usually for a concave mirror, it's going to be smaller than the original object, and you're going to get, well, it's given by, well, the height difference, right? And that ratio is the same as, well, the object or the image distance divided by the object distance, right? So you've got these 3 equations that you have to kind of utilize when we're talking about concave mirrors, right? Any questions with this? Had to do ray diagrams? Yes or no?
I have a question.
Yes, Natalie.
What's P and Q again?
P is the object's distance from the back of the mirror or to the mirror, whereas Q is the distance to the, or it's the image distance. Thanks for asking that question. I haven't written that anywhere in the presentation.
Thank you.
Right, and then again, H is your image height, or sorry, your object height, and H, this little dash here, H dash is your image height for the magnification scale right here. Right? And well, the same principles apply to your, well, convex mirrors. So right here, again, you've got an object here. For that object, you will first draw a line that is perpendicular to your surface of the mirror. So it's this 3 here, that's perpendicular. The next one is that you could draw a line anywhere, basically, to the surface of the mirror. The way that that line is going to be reflected, or that ray of light is going to be reflected, is by drawing a perpendicular to that point on the surface of the mirror and measuring that angle, and that it's going to be reflected back, or reflected with the same angle as the incident ray of light to the perpendicular line on the mirror. Once it's reflected back, you can extend those back wherever those 2 lines intersect. That's where the object will be, right? And that's how convex spherical mirrors operate as well, right? And the important rule then is, well, that you've got these magnification rules, or, well, will the image be a real one or a virtual one? And what that basically means is that, well, would it be in the virtual space, or behind or inside the mirror, or will it be kind of in the real space or inverted? And that's where the sign comes in. So if you've got a plus sign with the magnification, your image is a virtual one and it's going to be an upright one. If you've got this negative sign, that means is that you've got an inverted image, and it will be portrayed, or it kind of will be seen, or it will form in the real space, right, or towards the actual object, not beyond that virtual space of where that mirror was, right? Any questions?
Would magnification have any units on it?
No.
Okay.
Again, remember, magnification was what? Magnification was the ratio of the either the object distance to the image distance, or the object height to the image height, right? So since they are both measured in meters, it's going to be, they're going to cancel out, so it's not going to have a unit. That's why sometimes you see that when you see that the magnification factor on your cameras are, well, times 2, times 3, times 4, so that means that it's been magnified as many times.
I had a question.
Yeah.
So, if it's positive, it's like the upright virtual, and if it's negative, it's inverted real, or is like
Yes.
always? Okay.
Right? So let me move on to the other presentation. So let me switch quickly. So what I'd actually planned for today was part 5 of the lecture, or part 5 of this PowerPoint, or the waves topic, and I don't know if you'll be able to cover this today because we've got 6 minutes remaining in class. But next part that we were going to talk about is the refraction part, or the fun part where you can kind of create colors from light waves. And the way you do it is you get this little prism which is able to bend light, or it's got a photographic film inside, and that's able to create this spectrum of light colors. And that's what happens with your rainbows and water droplets within the air. But more importantly, refraction is the bending of light as it passes through one medium and then goes to the other, or moves to another medium, right? So the more important part is that it should be incident at an angle other than 90 degrees, so it shouldn't be perpendicular to the surface of the mirror. If it's at 90 degrees, it will pass straight through and it won't bend. On the other hand, if it's at any angle of other than 90 degrees, it would bend, and it would create these colors, or the light wave would just bend, and it would give you a fake sense of height or whatnot. And that's what you see when you're standing in water, that your image inside the water is distorted, and that's because you've got light waves that are bending through, because you're passing from one medium to another medium, or your light waves are passing from the water to the air, right? And that's all because of refraction. Now the refraction happens because, well, every object has got a different density, so the waves are going to travel through that medium at a different speed. Remember what we talked about, the 2 rules for waves, that the speed does not change within the medium, but upon coming on contact with a medium, what happens to the frequency? The frequency remains constant, but everything else is it's changeable. So when we're talking about this and that part, when you're moving from, well, air to ice air, you've got a different density medium, so your speed would change. Why would your speed change? Because, well, your frequency, although your frequency is the same, you're moving through a much denser object. Your wavelength usually reduces when you move to a denser object, and in order to compensate for that, your velocity would reduce. And that's where your index of refraction, or this letter N, comes in, and that's essentially the ratio of the speed of light in vacuum to the speed of light in the medium. Now for air, that is 1. So air moves, or light moves through vacuum and air pretty much at the same speed. It doesn't vary as much. There's a slight, it's usually 1.000029 something, but we just take it as 1 to keep everything simple. But everything else, so it bends through, and the reason it bends through is because, well, it's got velocity to compensate for, because it's moving through a much denser medium, so it's kind of slowed down when it moves through a denser medium. But since the frequency is the same, remember, what was the formula for wave speed and frequency? It was related by the wavelength. So your velocity of the wave is what? It's the product of the frequency of the wave and the wavelength of the wave, right? So V is equal to F lambda. So if your frequency is constant, your velocity is slowed down, your lambda must reduce to follow that equation, right? And then we've got, well, and that's how this whole scenario happens, where you've got this distorted view of an image forming. So you've got a light wave that is traveling from the fish. It will bend in air, and what you see, or what the observer would see here then, is this little, because the observer will think that the light is passing through, or the ray of light is following a straight line, and it's going to give you this little apparent position or a distorted image of the fish, or that it's a higher location than its actual position in the water, right, based on this image. And that's what you see when you're in the swimming pool, but that's what you see when you're in the water, or that's what you see in kind of those distorted, not distorted, but let me think of another example. I can't really, but that's what you kind of use within your camera lenses as well. That concave shape, that's essentially where the lenses part comes in, and that's using refraction angle. Let me quickly go over this. So, and that refraction comes in, or it's known as the Snell's law, and that Snell's law is essentially the ratio that you're able to measure how the angle would behave, or how the angle changes, or what the angle of refraction is going to be based on the refraction index, or this letter Ni or N. And that simple relation is, well, it's the product of the refraction index and the sine of the incident angle of light ray equals to the refractive index of the medium and sine of the refracted angle, right? And you can kind of use this to calculate, well, what the angle is going to be, or how much the light would bend, right? Typically, when you're moving from a less dense medium to a higher density medium, the light would bend towards the normal line here, right? When you're moving from a dense or a high density medium to a low density medium, your light would bend away from this line that is perpendicular to the surface of the mirror, right? Now we're kind of gone over time. Let me just quickly scroll through, but it's mostly to do with, yeah, your equations won't change what you saw for magnification factor. Once we come back, we'll kind of do this more. We'll do a quick recap session after Thanksgiving off waves before we start on electricity. But you should be able to solve question number 2 and 3, which I'll post as in class assignment 5 for today. And that's kind of it. So I just wanted to go over this. There's no question related to internal reflection on the homework assignment, so I'll keep that off. But you can use this formula to find what the reflected angle is going to be and what the refracted angle is going to be based on the incident angle. And that's kind of it for today's lecture, right? Any questions? No? Well, if you have questions, please send me an email. Other than that, you only have 2 questions to do, which I'll be posting just now, or once this video is processed and uploaded to YouTube, so that link will be available to you. And then have a happy Thanksgiving. and take care.